So when we do the asymptotic algorithm analysis, so last Monday we learned that this kind of analysis, the asymptotic analysis of an algorithm determines the running time in peak O notation. So to perform the asymptotic analysis, first we need to find the worst case number of primitive operations executed as a function of the input size. So we learn about this one, the worst case number of primitive operations. So last time we already did the operation. Let me repeat one more time. So when we count the primitive operations, we have the operation like one operation, two operations, two operation, one, one, one. And in this case, we just need to have the worst case. In this case, the worst case is two operations, but we don't care whether it is 2 or 5 or some other numbers, because it is a number, then we can say that it is a constant. Regardless the data, how many data you have, it is always constant. But in this case, if the data increase, the number of operation will be depending on the number of the data. So it will be depending on the n. That's why this will be linear or n. So I don't care with this notation. I don't care with the operation. If the operation is for n plus 5, what is the big O? It will be On. Okay, we don't care about the constant here, and we don't care about this constant. We just need to know that this is the worst case scenario, which is n. And we express this function with big O notation. So last time we have the find maximum, so it is the On time. Since constant factors and lower order terms are eventually dropped anyhow, so we can disregard them when counting primitive operations. So you don't need to count the primitive operations when you want to find the big O. I show you how to calculate the primitive operations because you need to know how to calculate it to get the worst case analysis. Now we have another problem. We want to compute prefix averages. Okay, what does it mean by this prefix averages? So we further illustrate the asymptotic analysis with two algorithms for prefix averages. The I prefix average of an array X, it is the average of the first I plus 1 elements of X. So for example, I have the AI. AI, it will be the x0 plus x1 plus until xi, and it will be divided by I plus 1. Computing the array A of prefix averages of another array X has application to the financial analysis. For example, at the time 1, in the time 1, we have X. X is the red and A is blue. So the X is 21. When it is 21, yeah, the average is 21 because it has only one value. In the time 2, let's say this is January and this is February. So I want to get the average. What is the average? So if I look at the red color, here is the X, the value is about 23. Then I have the first value is 21, I have the second value is 23, so the average will be 22. So every time I would like to calculate the average whenever I come to a particular time. So when I come to time 3 or March, so I would like to again calculate the average, which is 8. So it means I have 20 plus 23 plus 25 and then divided by 3. If it is 21, 23, 25 divided by 3, then it is 23. So the average is here. So we would like to calculate the average for every of the time. Then this is the formula. Okay. Now, how can you make the Python code? So this is the code. Again, you don't need to write the code now, but let's analyze. What is the operation? If you look at this one, the following algorithm computes prefix averages in quadratic time. How can we know it is quadratic? Okay, let's see. This is just a primitive operation. Okay, we have method name, and then we assign a sequence. So if it is the primitive operation, maybe it is 2 operations. And length s. So it is also 1 and 2 operations. So it is constant. A equals to 0 multiplied by n. What does it mean? We will create new list of n zeros. So if I have the s, if the length of s is 5, then I will make 0, 0, 0, 0, 0. So I will make 0 for 5 times. Then I can say that this one is 1 operation, and then there will be like n. For j in range n. Okay, this is a for loop. We will go from 0 until n. Then it will be n operation. The total equals to 0. So there will be 1 operation. So it's n. Okay. For I in range j plus 1. J plus 1. J will be depending on the value of j here, which is the limit of n. And it will be n times. So in this case, we will do n times, and when we enter this form, there will be another n. So we have the n multiplied by n. When we do this one, so it is total equals to total plus si. So this is 1 operation, this is 1 operation, and this is 1 operation. So it is 3. Then I can say this is 3 n multiplied by n. The last one here, it is on this section of the for loop. So the aj equals to the total divided by j plus 1. Then this will be AND operation because it follows the for loop in the above part. If you look at the worst case scenario, then it will be n multiplied by n. This n multiplied by n, it is same with the n power of 2. The n power of 2 means the quadratic. Okay. So the running time of the prefix average one is O, 1 plus 2 plus until n. So the sum of the first n integers is n multiplied by n plus 1 divided by 2. Okay, so if you know the simple mathematics, okay, if you have 1, 2, 3, 4, 5, 6, so the summation of this one, 1, 2, 3, 4, 5, 6 will be n multiplied by n plus 1 divided by 2. Then the prefix average one, it will be running at the worst case scenario n quadratic, like what we see on the previous one. Now I have another code. This is prefix average 2. Is it better than the previous code? It seems better, okay, but we need to look at the function. Okay. So the following algorithm use the internal Python function to simplify the code. What is the internal Python function? So let's see one by one. We have the method name and then we have the parameter. So it is 2 operations. Again, we have these 2 operations. We have n times, so it means yeah, n. And then we have loop n times. And then we have aj equals to summation of s from 0 until j plus 1. So if you look at this one, what is it? This is the slicing. So if you start from 0 until j plus 1, let's say j equals to 1, then it will be running 0, 1, 2. Okay, this is sum. Yeah, S is the array, so it means 0 and 1. Okay. If j equals to 2, then it will run 0, 1, 2. So if j equals to n, what happens? It will be 0, 1, 2 until n time. So this also do the AND operation in the worst case scenario. Then we have n for the for loop, and then we have another n, then this will be n multiplied by n. Because in the worst case scenario of this one, it will be n time. Then again, this one still on power of 2. Now we have the prefix average 3. This is linear time. Let's see how it works. So the following algorithm computes prefix averages in linear time by keeping a running sum. So the prefix average 3. We have this method name and this one. So it is 2 operation. This assignment and this method, it is 2 operations. Okay, we don't care about those. this is n, and then we have, okay, one operation, we don't care with this constant. Now we have this for loop. So this for loop will be n times, and then this total plus equal sj. This means that we have the total equals to total plus sj. For this operation, it will give you like one operation, two operation, and three operation. So it will be constant. So 3n. What about this? AJ, it is one operation. Assignment is another operation. Divided is another operation. And j plus 1 is another operation. So I have 1, 2, 3. So it is also 3n. So in the worst case analysis, we can get that this is n. So this runs at n times. So this is point. So which one is better? Prefix average 1, prefix average 2, or prefix average 3? The best one is number 3 because it shows the best performance. It shows the best complexity. You can run with the ON. The other algorithm runs with ON power of 2. So the complexity is higher. So we will choose the ON, or we will choose the linear time because it is much better for the computation. There is another terms for the big O. We call it, this is the relatives of big O. We have big omega and we have big theta. The big omega is using this symbol. Fn is big omega Gn if there is a constant C which is greater than 0 and an integer constant n0 which is greater than or equal to 1, such that the Fn is greater than equal to C multiplied by Gn. We call big theta is like this symbol. So Fn is big theta if there are constants C prime greater than 0 and C double prime greater than 0 and an integer constant n0 greater than 1, such that we have this formula. So C prime multiplied by Gn, it will be less than or equal to the Fn, and Fn, it will be less than or equal to the C double prime multiplied by Gn. This is valid for n which is greater than equal to n0. For the easy intuition, okay, maybe it is difficult to understand the mathematical. For the easy interpretation, you can say that the big O is Fn is OGn if Fn is asymptotically less than or equal to Gn. So if Fn is less than equal to, we can say like the big O Gn. This one. Big omega, Fn is omega Gn if Fn is asymptotically greater than or equal to Gn. And we have Fn is greater to or equal O Gn. big theta, we call Fn is big theta Gn if Fn is asymptotically equal to Gn. So we have Fn equal to O Gn. Okay. So the difference is only the symbol. So yeah, this is some examples. 5n power of 2 is big omega n power of 2. Is it true? Big omega, it means it is greater than equal to. So if you look, yeah, it is true. So if you want to do the derivation, okay, there is a constant c greater than 0 and an integer constant n0 which is greater than equal to 1 such that Fn is greater than equal to Cgn for n is greater than or equal to n0. So if you derive, you will get the c equals to 5 and then n0 there should be, yeah, 1 is also okay to do this function. What about the second? N power of 2 is big omega n. Is it true? In the big omega, we need to have equal to OGN. Okay. In this case, if you look at this one, the n power of 2 is greater than big omega n. Okay. Then this is true. There is a constant c. This is the same condition. This is the same condition. And we have c equals to 1 and n0 equals to 1. What about this? Of course, it is true because we want to have the equal function. Fn equal to the big O of the Gn. Because it is equal, then we can say it is true. So in this case, this is true, and this is true. Okay. Maybe there will be a question like this one. How can we count the operation? This is the Python code. So I give the result here. So A equals to 5. Okay, this is 1. B equals to 6. Okay, this is one operation. C equals to 10. So this is one operation. For I in range, it is 1n. Okay, this is n time. We have another for loop. So we have n from the first for loop multiplied by n from the second for loop. And then here we have 1 and 2. So 2 operation. So it will be 2 multiplied by n multiplied by n. We have 2 operation, 2 multiplied by n by n. And then we have also 2 operation, 2n multiplied by n. So after we finish, you can look at this for loop. Okay, we have n. Because the for loop here and this for loop is in the same outline. Then it will have n times. What about this operation? W equals, so we have 1 operation, 2 operation, 3 operation. We have 3 and it will run for n times. P equal multiply P. Okay, so in the worst case, it will be 3, okay, because the above is 3. So let's just make 3n. But you can assume that it is 2n, but later on, we don't have. The last one, we have only one operation, is 1. So if you try to calculate all the operations, okay, so we have 3 plus n plus 1, 3, 5, 7. So 7n power of 2, and then we have 1, 2, 3. So it's 7n plus 1. So the total will be like this: 7n power of 2 plus 8n plus 4. Based on our analysis of the big O, we have 7n power of 2 plus 8n plus 4. So we can remove the lower order. We don't need this one. And we can just disregard this constant. Then the result will be n power of 2. Okay. So regardless of these operations, you can just immediately say that this is on power of 2. You don't need to make the detail of this kind of operations. Okay. So that's about the algorithm analysis. So in this section, we are going to learn some of the algorithm design strategy. I will give you some introduction about some strategies, and then we will do some discussion on each of this algorithm design. So I will discuss what is the algorithm design strategy, and this section will be only about the recursion. The algorithm design strategy, we can have many algorithm strategy. So there are two fundamental components for finding the optimal solution for a computing problem. First, you need to formulate the problem clearly. So what is the problem that you want to address? And after you have the problem, then identify the appropriate algorithm design techniques based on the structure of the problem for an efficient solution. So there are some algorithm paradigm. We call it paradigm because this is the big concept. The first big concept is recursion. So we will learn in this section. There will be another kind of paradigm, we call it divide and conquer, dynamic programming, and greedy algorithm. Recursions. Okay, we will learn recursion. Recursion, it calls itself repeatedly in order to solve the problem until a certain condition is fulfilled. So it has base call and recursive calls. So we will look at the examples later. Divide and conquer. It means this kind of paradigm, it will divide a problem into smaller subproblems. So I have one problem, I will divide it into subproblem, and then I will do the solution for this subproblem. I will do the solution for this subproblem, and then I will combine it. That's the meaning by the divide and conquer paradigm. it then solve this of those sub-problems, and then finally we will combine to get the global or the optimal solution. There are some applications. We will look at those, some of those, not all. Okay, we will learn about binary search, merge sort, quick sort later. There are some other kind of algorithms for fast multi-Stressen matrix multiplication. Multi means multiplication, closest pair of points, and so on. The other paradigm is dynamic programming. So we will learn also this dynamic programming. It tries to explore the space of all possible solutions by decomposing the problem into a series of sub-problems. So this includes a series. So if it is divide and conquer, we will divide into different sub-problems. We can divide into different sub-problems, like this one. But for the dynamic programming, it is a series. So we will follow the flow. We will follow the flow. And then we will follow the flow. And then we will follow the flow. And yeah, we have a kind of series or sequence. And it then combines the result to compute the correct solution for the large problem. Maybe the first one, we will just follow the sequence like this. We will follow the sequence like this. And then at the end, we will return back to the original following the sequence. So divide and conquer versus the dynamic programming. The divide and conquer will combine the solution of the non-overlapping or disjoint subproblem. So it means we have problems. The two subproblems will be disjoint or non-overlapping. But the dynamic programming, the subproblems are overlapping, meaning that the subproblems share subproblems. So we will look at the examples later. So this is just the concept of the dynamic programming. And there is another kind of algorithm, we call it the greedy algorithm. So the greedy algorithm means we want to find the optimum solution from many possible solutions in every step. So we need to try for every possible. Let's say this one is the 3. So it tries to get the local optimum solution, which may eventually lead us to obtain the global optimum solution. Let's say I have this is a 3. It starts with 5. And then I want to find the maximum values. I want to sum all those values. And I want to find the maximum of the summation. So I can do the greedy algorithm for every possible numbers from the root, okay, we call it this is root, until the child. Okay, this is the child node. So for every possible solution, it means we will go from the root until the child, we will go until the child, we will go until the child, we will go until the child. And we want to find the summation which gives you the maximum. If I go for the first step like this one, 5 plus 7 plus 2, the result is 40. But is there any other maximum? There can be other maximum. So we try to find every possible step. So we will go 5, 7, and 1. Okay, this is not more than 40. So we will go for 5 and 3 and 17. Okay, this is more than 40. So this will be the new maximum. Means the maximum is now 25. And then we will go 5, 3, and 4. So it is not more than 25. Then we will get the maximum is 21. Because this is greedy algorithm, because we will find every possible solution. So let's focus on the recursion. What does it mean by recursion? The recursion means when a method calls itself. So I have to open an account. The basic definition of the recursion is Fn equals to Fn minus 1. So if you have the Python method, it will be something like this. Countdown, it is a method. Countdown I, it is a method. And then I will print I. And then I will do another countdown, which is countdown I minus 1. So it will be decreasing by 1. And then we will print. So let's say if I start with 3, then 3, I will print 3, and then I minus 1. So I will have this argument equals to 2. I will do this method 2, then I will print 2. Print 2, and then now I will again call the function countdown 2 minus 1. So I will do 1, and then I will print 1, and so on. It will be infinite loop. Okay. So the recursion pattern should have this. This means this is the limit, or this is the final condition. If I want to count down n and I print n, if n less than equal to 1, return. So we call this is the base case, means that the function will not go slower, it will not go lower than 1. So if it is lower than 1, stop. But if it is not lower than 1, we will do the countdown. We can look at the formula like this one. Fn, it will be empty if n is less than 1. If it is not, then let's do again the function n minus 1. So I can check. We have the def countdown. Okay, and then if n less than equals to 1, then return. If not, then we call countdown n minus 1. So this is a recursion. You can try. Sorry, let me put this one print n. Okay, so you can see the number. Now you have the countdown. Let's say I want to have 5. Oh. Then I will get 5, 4, 3, 2, 1. So it is similar with for loop. But now we have another kind of pattern. We call it recursion. So the recursion or the recursive, we call sometimes recursion, sometimes we call recursive method. It will have this case. Values of the input variable for which we perform no recursive calls are called the base cases. So there should be at least one base case. It means we can have many base cases. Every possible chain of recursive call must eventually reach a base case. So whenever you do this kind of recursion, whenever you do this recursive method, it should reach the base case. And we have the recursive calls. It means calls to the current method. And its recursive calls should be defined so that it makes progress towards a base case. So the classical example for this recursion is the factorial function. The factorial function means, factorial. We have n factorials. So let's say if I have 5 factorials, it means I will do the multiplication 5 multiply by 4 multiply by 3 multiply by 2 multiply by 1. So it is a sequence. Fn, it will be 1 if n equals to 0. If it is not 0, then it will be n multiplied by Fn minus 1. So if I have 5 factorial, I can make like 5 multiplied by 4 factorial. I can again decompose it into 5 multiplied by 4 multiplied by 3 factorial and so on. So I can make something like this one. Okay, I don't give this to, so I can make the factorial and then I can the basic idea for this n is it will be 0. It depends if you can, if you have the other problems, it can be 1, it can be 0, or it can be minus 1. Okay, and then if n is 0, then it will be 1 because 0 factorial it is 1. And then I can have else. So in this case, this is the base case. And then the else will be returning n multiplied by factorial n minus 1. If I want to run this one, because I have the return function, I have the return statement, then I can put into one variable. For example, fa equals to factorial 5. and then I want to get the FA. Then the result is 120. 5 multiplied by 4 multiplied by 3 multiplied by 2, then it is 120. For the visualization, you can look at this one. It is the recursion trace, a box for its recursive call. So when we call the recursive factorial for, when we call the for, we will call the for minus 1. And then when it is 3, we will call 3 minus 1, which is 2. When it is now in 2, we will call 2 minus 1, it is 1. When it is 1, it goes to 0, it will call recursive factorial 0. The base case mentioned that if it is 0, then return 1. Return 1. So after we have written 1, it will return back. So when it is 1, so it will return back and check what is this result. Oh, it is 1. Then it will be 1 multiplied by 1. We know 1 multiplied by 1 is 1. So it will return back 1 multiplied by 2. Then we get 2. 2, and then we will multiply with the previous number, which is 3. So we will get 6. Then we will multiply with the number that we get. It becomes 24. So that's the way the recursion will do. Okay, due to the time limitation, I think I will stop here. Okay, I will continue on Monday.